Harmful substances that may be present in aggregates include organic impurities, salt, clay, shale, iron oxide, coal, lignite, mica, and certain lightweight and soft particles. The performance history of an aggregate should be a determining factor in setting the limits for harmful substances. Test methods for detecting harmful substances, qualitatively or quantitatively, are listed here. Aggregates are potentially harmful if they contain compounds known to react chemically with Portland cement paste and produce any of the following. 1. Significant volume changes of the paste aggregates, or both. 2. Interfere with the normal hydration of cement. And 3. Otherwise harmful byproducts. Organic impurities may delay setting and hardening of concrete, interfere with interaction of chemical admixtures, reduce strength gain, and in unusual cases cause deterioration. Materials finer than the number 200 sieve, especially silt and clay, may be present as loose dust and may form a coating that may weaken the bond between the cement paste and aggregate. Coal or lignite are other low-density materials such as wood or fibrous materials in excessive amounts will affect the durability of concrete. Soft particles in coarse aggregate are especially objectionable because they cause pop-outs and can affect the durability and wear resistance of concrete. Clay lumps present in concrete may absorb some of the mixing water, cause pop-outs in hardened concrete, and affect durability and wear resistance. Mica is composed of flat plates that can either act as cleavage planes in coarse aggregate or as severely flat particles in fine aggregate. Aggregates can occasionally contain particles of iron oxide and iron sulfide that result in unsightly stains on exposed concrete surfaces. The aggregates should meet the staining requirements of ASTM C330, standard specification for lightweight aggregates for structural concrete. When tested according to the ASTM C641 standard test method for iron staining materials in lightweight concrete aggregates, the quarry face and aggregate stockpiles should not show evidence of staining. As an additional aid in identifying staining particles, the aggregate can be immersed in a lime slurry. If staining particles are present, a blue-green gelatinous precipitate will form within 5 to 10 minutes. This will rapidly change to a brown color on exposure to air and light. In addition, rocks and minerals such as some cherts, strained quartz, and certain dolomitic limestones or alkali are alkali reactive. The reactivity is potentially harmful only when it produces significant expansion. The reactivity of an aggregate is classified according to this table. The aggregate tested using ASTM C1293 standard test method for determination of length change of concrete due to Alkali-Silica reaction, or the concrete prism test, commonly called CPT. Because this test takes 1 year to complete, a rapid assessment test in the form of ASTM C1260 potential alkali reactivity of aggregates mortar bar method can be used to produce results in 16 days. ASTM C1260 is less precise in determining aggregate reactivity, having been found to exhibit false positives and false negatives. Reactions observed with certain dolomitic rocks are associated with Alkali-Carbonate Reaction, or ACR. Reactive rocks usually contain large crystals of dolomite, scattered in and surrounded by a fine-grained matrix of calcite and clay. ACR is relatively rare because aggregates susceptible to this reaction are usually unsuitable for use in concrete for other reasons, such as strength potential. Alkali reactivity of carbonate rocks is not usually dependent upon its clay mineral composition. Aggregates have potential for expansive ACR if the following lithological characteristics exist: clay content or insoluble residue content in the range of 5% to 25%, calcite to dolomite ratio of approximately 1 to 1, increase in the dolomite volume up to a point at which interlocking texture becomes a restraining factor, and small size of the discrete dolomite crystals or rhombs suspend in a clay matrix. The three test methods commonly used to identify potentially alkali-carbonate reactive aggregates are petrographic examination, ASTM C295, rock cylinder method, ASTM C586, and concrete prism test, ASTM C1105. Aggregate processing consists of 1. Basic processing, crushing, screening, and washing to obtain proper gradation and cleanliness, and 2. Beneficiation, improving quality of processing methods such as heavy media separation, jigging, rising current classification, and crushing. In heavy media separation, aggregates are passed through a heavy liquid. The heavier particles sink to the bottom while the lighter particles float to the surface. Jigging separates particles with small differences in density by pulsating water current. Rising current classification separates particles with large differences in density. Crushing is also used to remove soft and friable particles from coarse aggregates. Aggregates should be handled and stored in a way that minimizes segregation and degradation, and that prevents contamination by deleterious substances. Stockpiles should be built up in thin layers of uniform thickness to minimize segregation. Crushed aggregates segregate less than rounded aggregates, and larger size aggregates segregate more than smaller sizes. To avoid segregation of coarse aggregates, size fractions can be stockpiled and batched separately. Washed aggregates should be stockpiled well before use so that they can drain to a uniform moisture content. Bulkheads or dividers should be used to avoid contamination of aggregate stockpiles. Partitions between stockpiles should be high enough to prevent intermingling of materials. The discussion in this module began with the geology of aggregates. We then covered the classification and characteristics of aggregates, followed by potentially harmful materials. Some time was devoted to discussing alkali-aggregate reactivity, and then we wrapped up with a beneficiation, handling, and storage of aggregates. Please write down any questions you may have in your journals to bring and discuss in our next class.